I'm Pat Dugas. This lesson is about complex numbers, which allow us to solve some quadratic equations that have imaginary solutions. So it all begins with the mystery of the quadratic equation x squared minus 1 equals 0. Well, if we took x squared minus 1 equals 0 and we tried to solve it, we would duly use our addition property of equality, and that would yield x squared equals negative 1. Well, and then we would take the square root of both sides. And we would get this thing called x equals the square root of negative 1. Well, no number squared can equal negative 1. A square literally means we have a number like, let's say, 9, and we're trying to figure out what is the dimension of square that will make that number, and it's 3 times 3. Well, there is no negative number. There is no number that will multiply by itself to give us negative 1. And so to be able to solve this sort of quadratic, which does come up, humanity needed to invent a number to represent that. And so thus was born the idea of imaginary numbers, the biggest of which, the most important of which, is the imaginary unit I, which is the square root of negative 1. And that is a very important concept to remember. This is an imaginary number. It's created to solve the question, what is the square root of negative 1? And we can use that to build a whole system of numbers. If I to the first is equal to the square root of negative 1, well, if we multiply by I by itself, we would get the square root of negative 1 times the square root of negative 1. We would actually get negative 1. So I squared is negative 1. I to the third power, if we took negative 1 and multiply it by I again, we would get negative I, because negative 1 times I would thus be negative I. And I to the fourth power, if we took I squared, which is negative 1, and multiplied it by itself, we would get I to the fourth power. Negative 1 times negative 1 equals I. It's an interesting pattern. Every multiple, and this repeats itself in multiples of 4. So for example, I to the fifth would revert back to the square root of negative 1. I to the sixth would be negative 1. I to the seventh would be negative I, and I to the eighth would be I. And it continues to repeat itself. So some properties of it, but the biggest takeaway from here is we can solve the square root of negative numbers with this imaginary unit. So let's do a couple of examples. Let's take the square root of negative 28 and try to simplify that. You would treat it just like a regular positive square root, break it up into its factors, just use negative 1 as one of the factors. So the square root of 28 can be written as the square root of negative 1 times 2 squared times 7. We're always looking for, when we're doing square roots, we're always looking for perfect squares, and 28 certainly has one. So we can break this down. This becomes the square root of negative 1 times the square root of 2 squared times the square root of 7. These are properties of square roots. And of course, the square root of negative 1 we've defined as this special number I. The square root of 2 squared is 2. And 7 is a prime number. We can't do anything with that. So one way to write this is 2I times the square root of 7. More commonly, though, it's actually written 2 times the square root of 7I. So now we're going to look at another example here, a product of imaginary numbers. Let's take negative 3I times 2I. Well, we can actually multiply those out by multiplying the coefficients and multiplying the I. So it becomes negative 6 times I, which is negative 6I squared. But if you remember from the properties of I, if we take I squared and break it down, I squared is equal to negative 1 because I is the square root of negative 1. So it becomes negative 6 times negative 1, since I squared equals negative 1. And so our answer is just 6. Here's another example. If we take the square root of negative 12 and multiply it by the square root of negative 2, we're going to want to break up those parts. Well, okay, the square root of negative 12 times the square root of negative 2 is equal to I times the square root of 12 times I times the square root of 2. Notice we've eliminated the negative by including this I in there. We can actually combine some things here. I times I is I squared. Square root of 12 times the square root of 2 is the square root of 24. And of course, I squared is negative 1, one of our biggest properties. Really a very important property just to keep in mind with anytime you're working with these imaginary numbers. I squared is equal to negative 1. So The square root of 24, we're going to break it up into perfect squares. It's equal to the square root of 4, which is a perfect square, times the square root of 6. And so that becomes negative 1 times 2 times the square root of 6, or negative 2 times the square root of 6, which is our answer. So where the rubber meets the road, where this is really important, is to be able to find imaginary solutions to quadratic equations. So let's take 5y squared plus 20 equals 0. Without imaginary numbers, we can't solve this. So first thing we're going to do is let's subtract 20 using the subtraction property of equality. We'll subtract 20 from each side. And that gives us 5y squared equals negative 20. Okay, next thing we'll do is divide by 5. And that gives us y squared equals negative 4. Now we're going to take the square root of both sides. And thankfully, these imaginary numbers give us the ability to do that. Otherwise, there's no real number that's going to give us negative 4 when we multiply it by itself. And so since negative 4 can be written as the square root of 4 times negative 1, well, the square root of 4 is 2, and there is a plus or minus here, of course. The square root of 4 is 2, and the square root of negative 1 is I. Either plus or minus 2i are the solutions to this quadratic equation. So complex numbers are an expansion of the number system. Up till now, you've dealt in the real numbers. There's a completely different screencast and all kinds of information on the real number system itself. Complex number system expands that, including an imaginary part. So a complex number can contain a real and an imaginary component in the form a plus bi. Now, the first part, the a, is the real part, and the other part, the bi, is the imaginary part. Now, it's possible that a complex number could have a 0 real part, in which case it would be only imaginary. Likewise, a complex number could have a 0 imaginary part and be only real. You're familiar with numbers like 3. Well, in complex form, 3 is really 3 plus 0i. It's just we ignore the imaginary component. Let's look at an example of a complex number. Let's take negative 3 plus 7i. Well, the real part is negative 3, and the imaginary part is 7i. Both parts together constitute a complex number. So what we've looked at are we've built up imaginary numbers and complex as part of the complex number system in an attempt to help solve quadratics that have imaginary solutions.